So the question now arises is, how is nuclear magnetism generated? What is its basis? And we will here talk about the classical view, more on a classical view than the strict quantum mechanical view, but I will make some references to the underlying quantum mechanical theory. Now, it is known from nuclear physics that a nucleus typically has an angular momentum, which we know from our physics classes is denoted L, but here it is called P. So we can envisage we have the nucleus here, and the nucleus has an angular momentum. Now, we have with an angular momentum, classically, now we'll take here the classical view, classically we associate with an angular momentum a rotating motion. So we have a rotating motion, and we'll stick with the classical view because this gives us an intuitive feeling where the magnetism comes from. So if we feel like, in the description, that the nucleus is rotating, since the nucleus is positively charged, there is a rotation of the electrical charge. You can imagine this is like the Earth, it's positively charged, it's rotating, so at the equator the charge is moving, and moving charge implies a current. So here is the angular momentum, and since we have a rotating current, here's the rotating current, so we'll associate this with a rotating current, and such a rotating current now is associated with a dipole moment. It's just like a current. This is again the classical picture. It's not perfect, but it helps us understand where nuclear magnetism comes from. So we'll associate it with, just like with a ring current, with a dipole moment mu, that we will call mu here. Now, in terms of magnetism, we can picture the nucleus as if it was a bar magnet. The magnetism of the nucleus acts as if it is a bar magnet. It's not a bar magnet per se, but it acts electromagnetically like a bar magnet. It has a dipole magnetic field associated with it. So that's the intuitive reason why with some nuclei we have an angular momentum. Once we have an angular momentum, we have with it associated a dipole moment. Now, if we look at a magnetic moment of an individual spin in a induction field, so this dipole moment, this magnetic moment, is given by mu is equals to gamma times the angular momentum. And gamma here is called the gyromagnetic ratio. It's an empirical constant. There's a more profound theory behind it on what dictates the gyromagnetic ratio for a given nucleus, but we'll here, for our intents and purposes, it suffices to say that this is an empirical constant. Now, what we know from quantum mechanics is that the angular momentum of a nucleus is quantized. So it has for the z component of the angular momentum, it has two I plus 1 values, and they take on the values mi. So here is, for example, where I can go from minus the angular momentum, the z component, the quantum number m here, can go from minus I to plus I and increments in values of 1. So here in this particular example, we go from minus 3/2 to minus 1/2, plus 1/2, plus 3/2. That's the z component of the angular momentum. We can calculate the total angular momentum, and this is given by this equation here. So it's the quantum number, the angular momentum number here, I times I plus 1 times h over 2 pi. So if we take this for a spin 1/2, so the spin 1/2 can take the values 1/2 and minus 1/2 the angular momentum. In this case, the total angular momentum is times the Boltzmann constant times square root of 3 over 4 pi. That we can verify by putting here into I 1/2. So that's for a spin 1/2. So let's look at some isotopes and their gyromagnetic ratio gamma. And first, we want to introduce some isotopes that do not carry an angular momentum. Those are carbon-12, oxygen-16, etc. They have typically even mass and even atomic number. So they don't carry a nuclear spin, they don't carry a nuclear angular momentum. Then we have nuclei with spin 1/2. These are the proton, the hydrogen nucleus, H1, C13, and nitrogen 15. Another one is phosphorus 31. They are characterized by a spherical charge distribution in the nucleus. And then we have the spins that are larger than spin 1/2. Deuterium is an example, boron 11, sodium 23, lithium 6 is another one, lithium 7, etc. Depending on whether they have odd or even mass and an odd atomic number, they carry either half integers, so they're 3/2, 5/2, etc., or a whole integer, they're spin 1, 2, 3, etc. What's particular about these nuclei is that they have an ellipsoidal charge distribution. They generate within the nucleus an electric field, and it's a so-called quadrupolar electrical field. They have distinct different properties typically than the spin 1/2. Now let's look at some examples here. So we have the isotope listed. We have the spin, whether it's spin 1/2, etc. The gyromagnetic ratio. And here we list the gyromagnetic ratio not as the gyromagnetic ratio, but we divide it by 2 pi. So this gives us a number that relates the Larmor frequency to the the frequency to the Teslas. And finally, we have the abundance. So what do we see here? We have hydrogen spin 1/2. Gyromagnetic ratio is 42 megahertz per Tesla, and it's basically every hydrogen atom is a H1. Then we have deuterium. This has a spin 1, so it's a quadrupolar nucleus, very low gyromagnetic ratio, and the abundance is about 0.01%. Phosphorus 31, spin 1/2, gyromagnetic ratio is about 40% of that of the hydrogen, of the proton, and the abundance is 100%. Sodium, 100% natural abundance here. It's a spin 3/2, and gyromagnetic ratio is roughly 1/4 of water. Same holds for carbon 13, but the abundance for carbon 13 is 1.1%. And fluorine 19 is almost the same gyromagnetic ratio as protons, and the abundance is also very high. We just don't have a lot of fluorine in our bodies. Now, for reasons of the abundance and the presence, we will be mostly concentrating this course on considering the hydrogen nucleus, that is the proton, as the source of the MR signal. And for all intents and purposes, it suffices to know that there are other nuclei around, how to understand them, but most of what we are going to deal with is focusing on the hydrogen nucleus, that is the proton. It has spin 1/2. It has a high gyromagnetic ratio, and we'll see shortly why this is important, and what's also important, it is present in our bodies in raw abundance. So far I've explained that some nuclei carry an angular momentum, they therefore carry a magnetic moment, but now how does this generate a macroscopic nuclear magnetization? And that's the question we're going to address here. So let's look at the energy of a magnetic dipole in a magnetic field, in an external magnetic field, and we'll stick here to the classical description. The energy is given by the scalar product of the dipole moment with the external magnetic field, and it is given by mu times cosine. That's because of the scalar product, or if we say mu cosine, that is the z component of the dipole moment times B0. That is the energy of a magnetic dipole. Now, this energy is minimal when the magnetic dipole is aligned with the magnetic field. That is actually used. Where is that used? Or where was it used? Well, think about Christopher Columbus. He needed to know where the North Pole is, so he had to use a way to identify the magnetic North Pole, and this was done with magnetized needles orienting in a liquid parallel to the Earth's magnetic field. So that was used in navigation. Now, what's behind this is that a dipole will align itself to find the minimal energy, and there's a torque exerted on the dipole that is given by the magnetic dipole, the vector product of the magnetic dipole with the external magnetic field. So let's just demonstrate this in the following experiment, where we will demonstrate the force of the external magnetic field on the dipole with a magnetic dipole. As mentioned in the course, the energy of a magnetic moment, a nuclear magnetic moment in an external magnetic field is not dissimilar to what happens with a macroscopic magnet in an external magnetic field. And I want to illustrate this with this experiment here. We have a magnet here which can rotate, so it can freely rotate. Here is it's attached here to show the torque. And here we have two electromagnets. These two electromagnets will develop the magnetic field when I turn them on. So right now there is no force on this. The magnet is like this. And when I now turn on the magnetic field, you can see that the magnet tries to align itself. If we didn't have here this force meter, it would align itself perfectly with the magnetic field. If I reverse the polarity of the magnetic field, the motion is in the other direction in this sense. I can see if I can illustrate this. If I loosen this, then now here you can see the perfect alignment if I don't have the force attached to it, which is meant here to illustrate the development of the force. So like a macroscopic magnet in a magnetic field, nuclear magnetic moments have a tendency to align themselves in one direction or the other, and their energy that they have in the magnetic field depends on their orientation. But the minimum is found when the moment is as much aligned as possible with the magnetic field. Okay, now we have stated the energy as a function of the z component of the magnetic moment. So it's this term here, mu z times b0. So we will now look at the quantum mechanical description. And we know that the z component of the angular momentum, and therefore of the magnetic dipole, is quantized. It has discrete values and it's given by this expression. This is the gyromagnetic ratio, and these are the terms that we have introduced for the angular momentum just in the previous slide. So we have energies that depend on the level of the z component of the magnetic moment, that is the angular momentum. Again, mi can go from minus I to plus I. For a spin 1/2, it's minus 1/2 to plus 1/2. So if we set for spin 1/2, we'll take the energy level below. So that is minus gamma h over 4 pi times b0. Here's the energy level. This is for the m of 1/2. And we'll say there are n2 spins in that energy level. Then we have the higher energy level. That's where the dipole is opposite, in opposite orientation. Here the energy is now positive. It's spin 1/2, so it's plus minus 1/2. The calculation is given, so m equals minus 1/2. You can verify this with this equation here. I will say we have n1 spins in that energy level. We now have an energy difference, whether the nucleus, its spin is pointing upwards or downwards. It has an energy difference depending on its orientation that is given by the gyromagnetic ratio times Boltzmann constant divided by 2 pi times the magnetic field B0. Now we know from Boltzmann statistics, or the Boltzmann distribution, we know that we are going to get an unequal population of energy levels. This is dictated by Boltzmann distribution. And the relationship between the number of spins in the higher energy level, that is n1, to the energy in the lower, the number of nuclei in the lower energy level, this relationship is given by e to the minus the energy difference divided by the thermal energy, which is kT. K is the Boltzmann constant. Here is its value given. It's not really important. But what is important, if you look at this ratio and you do the math, you plug this in, you calculate the delta E divided by kT, at 310 Kelvin, which is roughly our body temperature, you'll find that at a field of 1 Tesla, if you look at the proton spins, so we take the gyromagnetic ratio of the hydrogen 1 nucleus, the proton, then you find that for every million protons in the higher energy level, there's a million protons, 1,000,001 proton in the lower energy level. That makes a difference, an excess in difference between the two energy levels of 1 out of a million. So basically, as a rough approximation, we can say N1 is the number of spins in the upper energy level is almost equal to the number of spins in the lower energy level, where N, and so we'll call this N over 2, where N is the total number of spins or hydrogen nuclei present in our voxel. So this is the Boltzmann distribution. Now, if we look at the situation here, if we are now looking at the distribution of the spins, we have them all in the lower energy level and none in the higher energy level. Is such a state even possible? Well, in theory it is. This basically means that N1 over N2 goes to 0, and this is if we let the temperature go to 0. Then e to the minus 1 over 0 becomes e to the minus infinity, that becomes 0. So if we cool our sample down to micro or nano Kelvin, we essentially are getting something that approximates this state. This is the ground state of the system. For us in biomedical imaging, this is not very interesting. We cannot really cool down our subjects for imaging. So if we raise the temperature now gradually, what we have is that the thermal energy will bump some of the spins into the higher energy level. And as we increase the temperature, we have more and more in the higher energy level. We'll still have a certain difference in the population unless we have the temperature go to infinity at very high temperatures. Then they are truly equalized. That we can see again here. If the temperature goes to infinity, this goes to 0. E to the minus 0 is equals to 1. So we have this population difference that is generated between the nuclei in the higher energy level and the nuclei in the lower energy level, and this difference is important. Before we go on though, I want to make the point here that we have also these transitions between the energy levels is induced by photons. Photon is the interaction boson for electrodynamics, so we can associate this energy difference here, the delta E, with a photon energy h nu, and then we can look this up, what this value is, to relate this to the X-ray techniques that we have been discussing in the first half of this course. And then we can see actually that for NMR, nuclear magnetic resonance or magnetic resonance, we have the energies are in this range. So they are in this wavelength range here. We are well beyond microwave wavelengths. So it's very long wavelengths. And what is important here, we are working with non-ionizing radiation in magnetic resonance.